going to do is, it is going to be about Sokolov spacing. So basically, when we are trying to solve these particular partial differential equations, you want to work in function space. So let's again go to simplest problem which we have been considering from day one. Okay, many of the things that we are doing for Laplace equation can also works for heat equation and wave equation. So if you study this thoroughly about the functional spaces and all that, many of the techniques can be extended. Of course, you have the time factor which appears, so one needs to take extra care of it. But for present, we are more than happy to learn about this. As we had said, and yesterday also we had got those examples. Here, when we are talking of harmonic functions, we have Laplace u equal to 0, and then we have seen that it is C infinity, and it is not only C infinity, it is analytic. Okay, so you should certainly look up examples, just out of curiosity, that there are functions which are C infinity but not analytic, just to understand the difference between real analytic and C infinity function. What do you mean by that? Okay. So here, if you have this, when I'm writing something like this, I'm writing delta of u. So in my mind, I'm always thinking that I want my function u to be at least twice differentiable. But as we have seen, we have been listening since yesterday, that set of C2 functions is going to be kind of very small to look for solutions. Okay. And it is better to kind of interpret this in a weaker sense, kind of weaker sense. So what do? We know that C infinity functions with complex support are dense in what? LP spaces. You all are aware of LP spaces. So these are already larger class of function spaces which you all have already seen. Okay, so let me just write down. So this is LP spaces. So what are these? What are these? Quick to define. This is tutorial. You will have to tell. F belongs to, what are these? What are LP spaces? The LP of omega. Yeah, so it is integrable functions, right? You want them to be integrable functions such that integral of mod f power p is finite. Okay, so this is a integrable functions with the property that integral mod f power p is finite. And what do we know? We know that this is a Banach space. With norm. What is the norm? What is the norm? Right? And what do we know? What do you mean by a Banach space? It's a complete nonlinear space. And in case p equal to 2, in case p is equal to 2, we know that it is a Hilbert space because you have an inner product. Okay, so what we will see quickly is that here, and I believe you have also shown that C infinity functions with complex support are dense in these particular spaces. Okay. So let us okay, here I'm just still going to consider derivative problem. Okay, what we are familiar with. So this is n omega open subset of Rn on boundary of omega. What can I do? I consider C infinity function with complex support, okay, and multiply both sides. So we take Laplacian u phi equal to f of phi, multiply both sides by phi and integrate over omega. So here the matter. If you put Laplacian here, I want to do integration by parts. So quickly do integration by parts. What is Laplacian of u? What is it? See, one really doesn't need to think of Laplacian as a whole. You can think of just one variable, right? Laplacian has d square by dxi square. So you square of d of dxi of u or phi, right? If you differentiate this is going to be what? D square xi u phi plus what? Di of u, dxi of u, dxi of phi. That's all. Right? So this is going to be, so this if I sum over I, it is going to be my Laplacian. Right? So this is going to be this minus this. Okay? So this is going to be on the boundary term. Right? Minus so here we have 1 to n. So here you can apply your Green's theorem. Okay, and what do you get? This is equal to integral of gradient u dot n times p on boundary of omega, right? Your phi is function with complex support, so it is going to be 0 on the boundary. So this term goes away. So this is equal to 0, and we get so here what we have done, this problem, this particular problem is equal to solving phi. So we are looking for u with the property that this holds for all phi and c infinity functions with complex support. One can calculate this. And now we see we no longer require our u to be C2, we can just require it such that integral of gradient u is finite. Alright. So if usually you want to apply the Holder's inequality, so if L2 norm is finite, all these quantities are going to be fine. So this is in L2 and if this is in L2, you can try to solve this kind of equation. Okay, so that is why even when we were trying to see our problem, we usually consider this kind of energy function. Okay, we want to minimize it later on. So here we want to say that instead of finding u in classical sense, that is a C2 function, we can look for u which is going to satisfy this particular equality. Okay, we say, and then if we are able to show this is smooth. Okay, if we are able to show from various estimates or from PD theory that actually U is smooth or it is C2, then we can retrace back and go back to our Laplace equation. So what we have done is we have reduced the regularity condition on the solution set where we are looking for solutions. Here I don't require U to be C2. I will be more than happy if I have gradient of U is in L2. I also require U is in L2. Just so that I'm in nice space. So this is what uh, is in fact what is called as weak solution. Okay? So if we are able to find U in some space, I have not defined that space as yet, but if I'm able to find U such that this particular equality is satisfied, then U is said to be a weak solution of the given differential equation. So I will write down the definitions. That's fine. So, so this is phi is anyway L2 because it is a smooth function with complex supports. Okay, so we get this. Okay. So this brings us to the concept of weak derivative. So here I said it is a weak solution. I want to use the similar motivation to define what is weak derivative of a function. So here, so again, when I say L1 low, it is going to be locally L1 function in a given function of a point. It is L1 and alpha up. So alpha is alpha 1. So here, what am I trying to say? See here, when I was trying to solve this problem, when I look for the solution, I just require this integral equality to be satisfied, and I only require to begin with that this particular quantity is in L2 space. So it can make some function B. Then later on I will find out its smoothness and all that. So that kind of function which represents the gradient of a function, derivative of a function is called as weak derivative. I'll make it clear on here. So here a function B is said to be weak derivative of u. So I will just give first derivative. If it satisfies what? Integral of so here can you see it? Or it's not there? So here I'm just doing alpha I derivative. Okay. It is just alpha I derivative. And what have I done over here? I want to differentiate u. I know maybe it is not differentiable in our usual sense. So I will multiply it by 5. I will push the derivative which I want to do on u on the 5. Okay. And if I can find a function v which is in the space which we require such that this quantity is equal to this, then phi is the weak derivative of u. Okay. Understand? So here let me tell you. Okay. So here what are we doing? If my u is differentiable, then I can do integration by parts. Okay. If u is differentiable, or if u is differentiable, my di of u is defined, right? So what do I mean? Di of u p is equal to minus integral of u dit. Why? Because phi is continuous function, C infinity function with complex support. So again integration by parts will mean that this is nothing but, okay, this is equal to this. This is just my integration by parts. So now what I am doing, when I want to say that u is weakly differentiable with respect to I coordinate, what I am saying is I am just looking at this part over here. Okay. I am just looking at this differentiation, this particular thing, and I am saying that if I can find a function v such that this particular equality holds for all phi, then v is going to be my weak derivative. So I am not differentiating v, I am differentiating this and I am defining it as weak derivative. This function is the weak derivative of v. It is an easy exercise to state that if u is actually differentiable, then the weak derivative coincides with usual derivative. So can you see why quickly? Why is it true that weak derivative is same as usual derivative? U is differentiable. Why is it true? Yes?
Can you see that? I can move. There.
Why is the weak derivative same as? Because when I say weak derivative, it is a function, right? And if I am given two L1 functions, there is no uniqueness. Two L1 functions can always differ by set of measure 0. The integral is not two element functions can become a set of measures 0. But when I define derivative of a function, it is well defined quantity, right? It is not up to a set of measures 0 or something like that. So here, if I want to show that, how do I show? You understand what is the question, right? Any ideas?
Every of V is equal to
V, right? But why is that true?
minus
Why is that true? Because if u is going to be differentiable, then whatever I did here, I will do here, right? And I will take it as what? Minus integral of dru phi over omega. So what do I have? I have this is equal to this. Is that enough to say that V is equal to dru?
almost
Yes. Is it enough to say that V is equal to dru?
Equal atmost everywhere. Almost.
Why?
integral
They're saying that integral over omega function multiplied by every test function is equal to 0.
Yes.
So this part
That can happen only.
is
And the set of test functions is dense in your set. Okay, that is why you get uniqueness. Because phi can converge to di of u, right? So then you can take norm and you will get equivalence. Okay. Is it clear? You have to do it in 2 steps. Okay, first of all, this is true for. So here I say it many times because this is just diu phi is equal to in your L2 inner product. Okay, so it is easier always when you think of it as inner product and it is over a dense set. So hence they will be equal if di of u is actual derivative. There is no escape. Yeah. So this is what we have done here is given a notion of weak derivative. The function itself may not be differentiable, but it is what is called as weakly differentiable. So here when we are trying to find this kind of solution, we are here looking basically for weak derivative. Okay, so not only that. So here we had just di. You can have gradient of u. And then in general you will have, so I have written here multi-index alpha, then you say that so you say that it is of weak derivative of multi-index alpha in same. equators and generalization. If you differentiate it twice, then you will have minus or minus 1 cancels and all that. So the weak derivative definition of general multi-index is this, and most of the time in the lectures, whenever you are talking of, I will define immediately, whenever you are talking of derivative, it's usually in weak sense. Okay? So though we are writing gradient q, you mean gradient q belongs to L1, some function which is represented, and that is why when we find a solution, like see Hendrik was minimizing gradient of u square. He was minimizing gradient of u square. Okay, and gradient of, to minimize that, what do I need? I only require gradient of u is in L2. I only require gradient of u is in L2. I don't require anything more than that. So if I want to go back to my Laplace equation, I have to prove regularity. I have to show that u is actually differentiable so that I can do integration by parts and get back to my original differential equation, because the physical problem is modeled using the differential equation. This is something which we have done to work in our space, in a larger space. So here this is definition of weak derivative. And as I said, this if exists. So and this doesn't mean that every every function is need not be differentiable. So here also, when we are talking of weak derivative, it is not necessary that you will always be able to find the candidate v to satisfy this particular integral equality. So you should see that example in Evans, where we have given example of a function which is not weakly differentiable. So you can take a look and so maybe L1 or L2. So you can check, you can have better some LP space also, and then you can say that it is some weakly differentiable function. So here so almost everywhere. So until we can say if I have two weak derivatives, then they differ by set of measure 0. That's what we said over there also, right? So if the function is C2, then your weak derivative is going to be continuous, and then actual equality will hold. But here in general, we are only able to say that two weak derivatives, if they exist, are unique almost everywhere. They are unique up to a set of initial 0. So the proof is set. You are taking dot product with respect to a dense set. Okay, so you can. So now I will define the Sobolev space. of F locally integrable functions which are property. Such that d alpha of F belongs to LP of omega for all mod alpha less than equal to k. Okay. So when I write d alpha of F over here, it is going to be your weak derivative. Okay, because I am starting only with an integrable function. I cannot make sense of derivative of F. But what I do is I can certainly define weak derivative, and this is the solar space which we have been seeing till now. So it is bigger than LP or smaller than LP? It is going to be, yeah, it is contained in and in fact one can show that there is a Banach space with norm. Because it's kind of interesting.
Something for the
Yeah, that's the easier way. But as usual, you can have the Euclidean because you are dealing with function space and this is slightly like your Euclidean norm. Okay, and then in fact you should prove that it is same as sum of LP norms of all the weak derivatives. That's easier, always easier to work with. So you can verify that as well. Equivalent to so that is some norm and that is similar to the Euclidean norm. So it is a good exercise to prove that these two norms are equivalent. Yeah. So that's always easier to work because we are always working with LP spaces. So, yes? Yeah. So coming back to our problem that we are faced.
The truth is the entire thing raised to
No, here it is individually raised to 1 by 2. That's some norm. That is some norm. That is like Euclidean. That's all. Yeah. That's like you have max or soup.
Right.
Some. This is some norm is easier. That's what you should. This some that is like Euclidean. You have already shown. It really doesn't matter what is underlying, whether it is underlying Banach space or what. I mean function space or what space. You can just take two Banach spaces, define one norm like this, define another norm, and then you can check which are equivalence of two norms. is some movement. So here, let us go back to you want to write. So here, let us go back to what we are trying to solve. I have shown this is equivalent to trying to find a weak derivative of my function u with a property that is the same as integral of f for all phi belongs to C infinity functions with complex support. So here, remember what has happened is I want u to satisfy Dirichlet condition. Okay, and if I'm only going to assume u is L1 or u is L2 or LP, what do I mean by u is equal to 0 on the boundary? Okay, it's something which is defined almost everywhere. Unless a function is continuous, you will never be able to write ux is equal to something. This is something which one needs to get used to, because when you are talking of L1 space, LP spaces, all those function spaces, you are always talking of almost everywhere. Whereas when we are trying to solve the problem, we want specifically that u is 0 on the boundary. The Dirichlet condition is u is 0 on the boundary. So how do you try to get that? So for that what we can do is the following, or at least try to improve or try to approach our goal. What we can do is this is a Banach space which we have defined. We know that C infinity functions with compact support are going to be in this particular Banach space. What we can do is define W0 Kp of omega to be equal to closure of C infinity functions with compact support in omega in Wkp omega with respect to the norm So what do you mean by closure of a set? What do you mean by closure of a set? Limit one, right? So what I'm saying is we already know the C infinity functions with complex support are contained inside WKP, this particular Banach space, and we are going to take the closure of that particular set with respect to the distance function, which is defined using this particular norm. So WKP KP0 omega, it is going to be a subspace, and by definition it should be a closed subspace of WKP omega. Okay. The slide, what we now see is that all these functions, because they are C infinity functions with compact support, they are going to vanish near the boundary of omega. Okay. Okay. Your omega is an open set, and if you are taking C infinity function with complex support, then it is going to vanish on the boundary of omega, and then in that sense we are expecting that the limit points of these functions will be vanishing on the boundary of omega in some sense. See, we cannot, like p equal to 0 on the boundary is well defined concept because it is a smooth function, but the limit of all these p's is just going to be again a function in WKP. Who said it is going to be smooth, right? But still we are trying to say that okay, all these functions are 0 on the boundary, and then we can think of the limit points of these smooth functions as kind of being 0. Okay, they are not exactly 0, but you have a feeling that it is going to be zero, particularly all these p's are going to be zero, and then what we can do is try to look for our solution to Dirichlet problem, not in WKP omega, but WKP 0 omega. Okay. And since as we have already seen, means you don't require LP, where you can take P equal to 2 easily. That's what we have been doing, because the holder continuity will immediately say that holder continuity. Sorry, the holder's inequality will immediately say that if I assume U is in L2, gradient of U is in L2, then I'm able to do. So what we define is this particular space and look for solution of Dirichlet problem in this one. Okay. So if we n tends to infinity, and of course these are generally differentiable function, infinitely differentiable function, and they are not going to be zero over here, right? They are zero, their derivative is also zero, the differentiable is zero. So what we can expect is d alpha of u should be 0 on boundary of omega. That is what one expects, and in fact for k minus 1. Okay. Because usually what happens if I take k equal to 1, if I take k equal to 1, I'm talking about first derivative, right? And when I approach the boundary, I really cannot differentiate there. I can only expect continuity. The regularity, when I try to do things on the boundary, the outside directions are missing. So my regularity reduces by 1. So this is what one should expect, and in fact this can be made precise. If you are interested, you can see there is a thing which is called as trace theory, where they show in what sense this holds for functions in WKP 0 of omega. So how the functions really look. Okay, you can use geometry, and you can map part of this upper half space, and then you can see in what sense this is equal to 0. Okay. So you can refer to the ones. So here first I have written just norm. This is for 1 less than equal to 1 less than equal to 3 less than infinity, and just that we have in L infinity on p equal to infinity of omega. consists in terms of essentials of the one that is the infinity of point. Okay. So I will list down properties. Again, you will have to work it out. Okay, I will just say some of the things which are important. So showing WKP is a Banach space. So you remember how you all proved that your LP space is this Banach space? How did you show? That was yeah. So basically, the proof could be very similar to how you did for this space, but you should write it down because you also have this how do you say, maybe you do it twice. See, suppose I'm having W1P. Okay, I'm having W1P. If I'm having W1P, then what do I have? The norm consists of LP norm of U plus LP norm of derivative, but that is weak derivative, right? So that is also a function which is in LP. So you are having sum of two norms. Sorry, you are actually having sequences of two functions which are in LP. So you have U, UN, and you will also have D of UN. But D of UN is another, say, Bn, which is a function in LP. So you are applying your completeness of your LP function to not only U but also this the derivative. And in the end, what do you need to show? So by my LP theory, I may be able to I will show that from my LP theory, I will show that my UN converges to U bar. Okay, and I will show that my Vn converges to V bar, but I still need to show that D of U bar is equal to V bar. You follow? Do you follow? So what I'm saying is, what I'm saying is that if I'm having a convergence sequence for UN in say W1P omega, so if I will take a Cauchy sequence and I want to find a convergence subsequence, right? So if I take a Cauchy sequence in this, I will get a Cauchy sequence UN in LP. I will also get a Cauchy sequence D of UN, which say I denote by Vn in. So I am having two Cauchy sequences in LP space. LP space is a Banach space, it's complete, so every Cauchy sequence is convergent. So I will get that this converges to U bar, I will get this converges to V bar, but I want to show convergence in my W1P norm. That also means that I need to show that this V bar is equal to weak derivative of U bar. Okay, so it uses your property of LP space, but there is something more you need to see to show it. Okay, so it is not difficult, and you should do it as an exercise. Okay, this is your functional analysis, whatever your measure theory, whatever your functional. Most of it is functional analysis. Okay. Yeah. So this is an important observation. You also this is necessary. can you have this is important property if omega is contained in Rn is bounded, then is a strict subset. The inclusion is strict in case omega is a bounded domain. If omega is equal to Rn, then both the sets coincide. Okay. So if omega you can verify this. And just as we have input space for p equal to 2, wk2 of omega, which is denoted as hk of omega, it has a special notation, Hilbert space, and w0 k2 of omega, which is hk0 of omega, are Hilbert spaces. Okay. And what is the so-called example for inner product of ub is going to be equal to summation of inner product of d alpha u d alpha b mod alpha less than equal to k. I am allowing alpha to be equal to 0 elsewhere. So it is natural inner product. It's
HK is defined.
Huh?
HK.
no, it is a notation. When p is equal to 2,
Exactly.
when p equal to 2, this is a standard notation that people denote it by hk of omega, and if it is completion of the C-infinity functions with complex support, then you have hk0. So this is the so let me just revise some of the things because he is doing regularity of rebound. Right? So you all know Lipschitz continuity. In fact, one of the things which I suggest you all do is because it's not done. If it is differentiable almost everywhere. So, in fact, Lipschitz functions are very nice for that reason. So, the concept of almost everywhere already appears when we study definition of Lipschitz, but of course, we don't know what it means by almost everywhere at that time. So, we only know like set of measures, finite sets, and those kind of so, but this is not very straightforward. Okay, you will see if you try to look up some proofs. You can ask Anuradha. There are some decent proofs which are nice and accessible, but otherwise classical proofs are like they use a lot of measure theory ideas to prove this. There is other notion also. If f belongs to L1 of 0, 1 and for f belongs define g of x or g of t to be integral 0 to t f of s ds, then g is absolutely continuous and g prime is equal to f almost equal. So what does this remind you of? Fundamental theorem, right? You have fundamental theorem, integral calculus, right? But the only thing is that it is not Riemann integration. Yeah, I am not saying f is continuous. I am saying f is L1. So the integral on the right hand side makes sense, and I am still using the definition of indefinite integral to write that particular function g. And still, whatever we proved for in that fundamental theorem still holds. Okay? Instead of having a g differentiable, here you get it to be absolutely continuous. So here, not only it is absolutely continuous, it is going to be kind of weakly differentiable, right? Because you are able to say that g prime is an L1 function. Okay. So this kind of function. So what do you mean by absolute continuity? Yeah, we see it only one time, right? Sometimes we see it and then we really never bother to look at it again. But when you do so much and when you do measure it, because so here absolute continuity. Yeah, absolute continuity means that if you have a finite set of intervals such that summation of mod of yi minus xi is less than delta. So then summation of mod of fyi minus f of xi is less than epsilon. And that is what it means by saying that the function is absolutely continuous. So here I mean g is absolutely continuous. If you take smaller and smaller this kind of partition, okay, and if this sum of the length is less than delta, then the sum of the image set is also less than epsilon. So basically what it means is that it takes set of measures 0 to set of measures 0. Right? So here if I am having, if the summation becomes small, then that one also is going to be small. Okay, if I give epsilon, then if I take finite partition, it becomes smaller. Okay. So and then so this is kind of a way of getting complete derivative, but I think I don't know whether Henrik will be using it, but I will forward you the notes and just in case of you are curious or once in a while we want to see the definition, we will check it. So let me go to I already mentioned about the completeness of this particular set. What about the dual space of these Banach spaces? Okay, you all studied dual of LP spaces. See, when we are trying to solve our PDE, we are minimizing certain functionals, right? And minimizing functionals means what? You are having linear functionals which are on function space. Linear functionals on function space means it is an element of dual. Okay, what do you mean by LP star? It is a functional, right, on LP. And what are we trying to do over here? We are trying to, like as you have seen, he wrote something like this, right? Or just function greater than zero, minimizing this functional, right? So here when you are trying to minimize a functional means what? You are trying to find, so this is defined on certain function space. J itself should belong to star of whatever Banach space that you are considering. So here when we are having these function space W0, K, P, omega, and we are having functionals which are defined on these particular sets, okay, then we need to find out where those functionals are lying or whether there are going to be nice representation. We know LP star is LQ where 1 upon P plus 1 upon Q is equal to 1, where in case P is not equal to infinity. Okay? Otherwise you have measures. If it is L infinity, then you have measures. Okay? So here one can think of what is dual of WKP of omega? That is what we want to think of. So here, what do we know? We know that LP, right? So if I take dual, then in fact, what do I get? It is a much bigger space than LP star. Whatever containment we had before, it is going to be opposite, right? And what we can see, of course, for L2 it is going to be easy. Because we are going to solve only for k equal to 2. So I will just remark what we have said. For k equal to 2 and p large enough, p greater than the dimension of the space on which the function is. So this is one can see that an element of has a representation in C0, so it is a continuous function. So we can expect. And think of so dual of continuous functions, and this dual, if you work out, contains the all Borel measures. Okay, so this is so I'm just writing this because just to show that usually when you are trying to calculate dual spaces of these Borel spaces, they can be very complicated. It is not easy to find out the duals straightforward. But for our Hilbert spaces, it is going to be easy. We can just use our D's representation here as well, and we can say the following. Functions f equal to f naught plus summation of I going from 1 to n d fi by dxi f naught f1 fn belongs to f2 of omega, where dfi by dxi is the weak derivative. correct. So here the dual space is denoted by h minus 1. This is denoted by h minus 1. So here when I write dfi by dxi in the weak, if the weak derivative means what? Integral of fi d of d by dxi of p is equal to some function times phi. Okay, so it's equal to some di or fi delta some minus 1. Right? That is what it means. Okay? So this is in the weak sense, and this is the no. So I think this should be power half. I think there is some. The proof is, as I said, by Green's representation here. So what do we have? We have f is a linear functional of h1 of omega, right? Yeah. What does it mean? If I want to apply, so linear functional is a linear map. It is a linear map of h1 omega to r. So what does this representation theorem say? This representation theorem says that every such linear functional is represented by a vector in that particular Hilbert space and in a product with that, right? So that is what this representation says. It says that any t function from x to I, you have t of x is going to be some gx, right? For all x belongs to h. So that is what we are going to use here. What do we have? If you are having a linear functional from here to this one, it's hk, this one. This one, this one. So what does it mean? By this representation here, you have f acting on any function f should be equal to, what do you want, g should be equal to inner product of the exist right? But now what is this inner product? This inner product is going to be what? What is this inner product? It is going to be your g